So think about the helium escaping your party balloon right now. The exact gas you'd use to float one of those bright red foil balloons up to the ceiling.
Right. Or, the same gas that scientists rely on to cool the superconducting magnets in a life-saving MRI machine.
Exactly.
Yeah.
That gas, that specific element, was actually forged deep in the Earth's crust by literally the heaviest, most intensely radioactive rock on our planet.
Yeah, and it's honestly one of the most profound paradoxes in the physical sciences. I mean, we naturally categorize the lightest, most ethereal elements and the densest, most inherently unstable elements into completely different mental buckets.
Right, they feel like they belong to totally different worlds.
Exactly. But geologically and physically, their origins are just inextricably linked.
And that connection is exactly what we are unraveling today. We are taking a deep dive into the hidden, completely astonishing, and frankly, billions of years long natural life of a single element, which is uranium. And the mission here, the goal for this deep dive, is to completely dismantle and rebuild how you understand this material. We are taking uranium entirely out of the modern, geopolitical context.
Right, the human context.
Yeah, we're ignoring human-made power plants, we're ignoring weapons, and basically all of 20th century history.
Because human interaction with uranium represents just a fraction of a microsecond on the element's actual timeline. It's nothing.
Right.
We want to trace its behavior in the wild, right? Where it's governed strictly by planetary physics, chemistry, and geology.
So we're looking at a huge stack of sources today. We've got geochemical research, encyclopedic entries on mineral databases, historical physics anomalies.
Yeah, and by going through all of that, we're going to map exactly how this incredibly dense metal successfully avoided sinking straight to the Earth's core.
Which is wild. And we'll get into how it chemically shapeshifts to navigate through underground aquifers, how it birthed the terrestrial helium supply you mentioned, and this is my favorite part, how it spontaneously engineered its own functioning nuclear reactors.
Billions of years before the first hominid even walked the Earth.
It is so crazy to think about. So let's start at the very beginning of the planetary timeline. We're talking roughly 4.5 billion years ago, because right out of the gate, uranium presents this massive physical contradiction.
It really does.
In terms of mass, uranium is an absolute heavyweight. It's roughly, 70% denser than lead?
Yeah, about 70%. Its atomic nucleus is just massive.
Right. So applying basic Newtonian logic, to the formation of the Earth, we run into a major accounting error regarding where all the uranium actually ended up.
Exactly. To understand why this is a problem for geologists, you have to visualize the Earth during the Hadean Eon.
Okay, paint that picture for us.
So shortly after the planet accreted from the primordial solar nebula, there was immense heat. Heat generated by constant asteroid bombardment and radioactive decay. And it caused the entire planet to essentially melt.
The whole thing.
The whole thing. It became a violently swirling molten ball of magma. And this triggered an event that geochemists call the iron catastrophe.
Right. And catastrophe here meaning like a sudden massive restructuring of the planet's layers.
Precisely. Because iron and nickel are very heavy and they were incredibly abundant, they liquefied. And driven by gravity, they just plummeted straight toward the center of the planet to form the Earth's metallic core.
Like a giant metallic raindrop just falling inward.
Yeah, exactly like that. Now, as this huge ocean of liquid iron sank, it dragged a whole suite of other elements down with it.
So they just dissolve into the iron.
Right. In geochemistry, we classify elements by their chemical affinities. The elements that dissolved into the sinking liquid iron are called siderophile elements.
Siderophile?
Yeah, which literally means iron-loving elements.
Okay, so things like gold, platinum, palladium, iridium.
Exactly.
And this is why those precious metals are relatively rare on the surface today, right? Most of the Earth's original budget for those metals is locked thousands of miles beneath our feet in the core. They basically hitched a ride with the iron.
They absolutely did. Now, given that uranium has a density of roughly 19.1 grams per cubic centimeter,
which is incredibly dense.
Far denser than iron, yes. So you would intuitively expect it to sink like a stone straight to the core, along with the iron.
Right. Gravity should have just pulled it all down.
But it didn't. The vast majority of the Earth's uranium is concentrated right here in the relatively thin, rocky crust and the upper mantle.
It completely defied gravity.
It did.
Which tells me that density is not the governing physical law here. It has to be chemical affinity overriding gravitational pull.
That is the exact mechanism at play. Uranium is categorized as a lithophile element, or a rock-loving element.
Lithophile. Okay.
Yeah. Despite its immense mass, uranium's chemical properties, specifically the configuration of its valence electrons in the outermost shells, make it highly reactive with oxygen.
Okay, wait, let's dig into that electron configuration for a second,
Yes.
because this is fascinating.
Yeah.
Why does uranium despise iron so much that it's willing to fight gravity?
Well, it comes down to the orbitals. Uranium is an actinide, meaning its highest energy electrons reside in the 5 orbitals.
The 5F orbitals.
Right. These orbitals are large, they're complex, and they're very diffuse. Now, metallic iron bonds by sharing a sea of delocalized electrons, but uranium's electron structure makes metallic bonding with iron highly energetically unfavorable, especially in a silicate-rich environment.
So they just refuse to mix.
Basically, yeah. Given the choice, uranium will violently seek out oxygen, which is highly electronegative and very happy to bond with uranium's available valence electrons.
Oh, wait.
So when the Earth was a molten magma ocean, the uranium instantly bonded with the lighter silicates and oxides.
So even though an individual atom of uranium is incredibly heavy, it essentially bolted itself to a giant, buoyant raft of silicate rock.
That's a great way to picture it.
It became chemically tethered to the lighter materials that eventually cooled to form the crust in the mantle, leaving the liquid iron to just sink without it.
Exactly. Solubility in the silicate melt completely trumped its physical density. The earth science literature we reviewed notes that while a microscopic fraction of uranium might theoretically be soluble in the core,
Like how much?
maybe 2 to 6 parts per million under extreme pressure, but the overwhelming vast majority partitions strictly into the rocky silicate mantle.
Okay, so it surfed the magma ocean, it stayed high up.
Right.
But even once it's locked in the rocky mantle and crust, it doesn't just spread out evenly. It plays another structural trick. And this brings us to some fascinating mid-1970s geochemical research from our sources.
Yes, this is a really cool study.
We looked at this foundational study by researchers Dostal and Capedri, and they were trying to figure out exactly where uranium hides inside solid volcanic rocks.
Yeah, their work was on the partition coefficients of uranium in rock-forming minerals. They were looking at alkali basalts from Sardinia and acid volcanic rocks from Tuscany.
Very specific locations.
Very specific. And they wanted to know, when magma cools and crystallizes into a solid rock, where does the uranium go on a microscopic level?
Really?
So to find out, they use this brilliant technique called fission track mapping.
I honestly found the methodology here almost as interesting as the result itself. I mean, how do you visually map an element that's only present in parts per million inside a solid chunk of rock?
Well, you force it to reveal itself using a nuclear reactor.
Which is such a flex.
It really is. You take a highly polished microscopic slice of the volcanic rock and you overlay it with a piece of specialized plastic or mica detector film.
Okay.
Then you place the whole assembly inside a research reactor and you bombard it with thermal neutrons.
Just hit it with radiation.
Exactly. Now, the vast majority of the minerals in the silicates, the iron, they just ignore the neutrons. But the trace amounts of uranium-235 scattered within the rock will absorb a neutron, become highly unstable, and instantly undergo nuclear fission.
So the uranium atoms are literally splitting in half inside the solid rock sample.
Right. And when they split, the two highly energetic fission fragments recoil away from each other at incredible speeds.
Oh, wow.
These fragments shoot out of the rock and they smash right into that overlying detector film, leaving microscopic trails of physical damage.
Like little bullet holes.
Exactly. We call them fission tracks. You then take the film, you etch it with a chemical base to enlarge the tracks, and you put it under an electron microscope.
That is so clever.
And the clusters of tracks give you a perfect, micrometer-accurate map of exactly where the uranium was sitting inside the original rock.
And what they found completely upends how you, or at least how I might picture a rock.
Yeah, it's very counterintuitive.
Because you assume the uranium is integrated into the beautiful, structured crystals that make up the basalt. But the major rock-forming minerals, the olivine, the pyroxene, the plagioclase feldspar, they were practically empty.
Completely devoid of uranium.
The uranium wasn't in the crystals at all. It was hiding almost exclusively in the glass.
And we should clarify for the listener that in petrology, glass doesn't mean, window glass.
Right, it's not transparent.
No, it refers to the ground mass. That's the interstitial leftover liquid magma that cooled so rapidly at the very end of the crystallization process that its atoms didn't have time to organize into a neat crystalline lattice.
It just froze.
It just froze as an amorphous solid between all the structured crystals.
So mechanically, why does uranium avoid the crystals? I was thinking about this, and it reminds me of trying to fit a massive, irregularly shaped gear into a really finely milled clockwork mechanism.
Oh, that's a perfect analogy.
Because as the magma cools, elements like silicon, magnesium, and iron neatly interlock to form these tight, highly ordered crystal lattices. But uranium is huge.
It is. Its ionic radius is massive.
And it carries a high electrical charge too, right?
Usually a +4 charge in these deep magma environments.
Right, so if you try to force that massive, highly charged uranium ion into a neat little slot meant for, say, a tiny magnesium atom, the structural integrity of the crystal just fails. It just doesn't fit.
It completely disrupts the lattice. Geochemists classify uranium as a highly incompatible element for precisely this reason. Its ionic radius and charge prevent it from substituting into the crystal lattices of those early forming minerals.
Okay, so imagine a massive underground magma chamber slowly cooling over hundreds of thousands of years.
Right. As the temperature drops, your olivine and pyroxene crystals begin to form. But because they absolutely refuse to incorporate uranium, the uranium is continuously rejected.
It gets evicted.
It gets pushed out of the solidifying crystals and dumped back into the remaining liquid magma.
Which means the longer the magma cools, the more concentrated the uranium becomes in the remaining liquid pool.
Exactly. This process is called fractional crystallization. As the heavy uranium-poor crystals solidify and sink to the bottom of the magma chamber, the residual liquid melt becomes increasingly enriched in all the bulky, incompatible elements that got rejected.
So it's like all the misfit toys getting pushed into one corner.
Exactly. And this remaining liquid is relatively light and buoyant compared to the solid crystals, so it gets squeezed upward through faults and fissures, migrating closer to the surface.
So essentially, over billions of years, the Earth has been operating this massive planetary-scale distillation column.
That's exactly what it is.
Melting, rejecting the uranium into the liquid phase, pushing the liquid higher, and repeating the process over and over, ultimately concentrating the uranium into the upper crust. It really makes the crust act like the Earth's attic.
The attic.
Yeah, it's the place where all the weird, incompatible, bulky elements get pushed up and stored away.
I love that. And that planetary distillation is remarkably efficient. Because of this continuous upward pumping of incompatible elements over geological time, uranium is astonishingly common in the upper continental crust.
Yeah, the encyclopedic data we reviewed points out a staggering statistic. It says uranium is roughly 40 times more abundant in the crust than silver.
Which is wild to think about.
It is. Because if it's 40 times more common than silver, you would think we'd be tripping over it everywhere.
Right.
Why is it considered this strategic, difficult-to-acquire metal? If it's so abundant, why aren't we just scooping it up out of our backyards?
Well, because abundance does not equal concentration.
Ah, okay.
While there is a vast amount of uranium in the crust globally, it is smeared out infinitesimally thinly across almost all granite and soil. A typical chunk of granite might contain maybe 3 to 5 parts per million of uranium.
Oh, wow. That's nothing.
It's nothing. You cannot economically mine rock at those grades. For uranium to be useful to humans, or frankly, for it to do anything highly anomalous in nature, you need a secondary geological process to gather it from its dispersed state and pack it tightly into a localized ore body.
That transition from a widely dispersed trace element to a highly concentrated ore that requires nature to set a very specific chemical trap.
It does.
Which brings us to the profound sensitivity of uranium to its chemical environment, specifically regarding oxygen.
Right. The secret to concentrating uranium really lies in its variable oxidation states. Uranium is highly redox sensitive.
Redox meaning reduction oxidation.
Exactly. Meaning its behavior changes drastically depending on whether its environment is oxidizing, meaning oxygen is present to strip electrons away from it, or reducing where electrons are added back.
So it's essentially a shapeshifter. Let's walk through the mechanics of that for the listener because it's so important. Say you have some trace uranium locked in a piece of granite near the surface. And rainwater, which has atmospheric oxygen dissolved in it, slowly percolates through the rock. What exactly happens to the uranium atoms?
In the presence of that oxygenated water, the uranium atoms undergo oxidation. They lose 2 electrons, transitioning from their insoluble +4 valence state to a +6 valence state.
Okay, so they lose electrons.
Right. And in this oxidized +6 state, uranium bonds with oxygen to form what's called the uranyl ion. And the uranyl ion is highly soluble in water.
Highly soluble.
At that moment, the uranium actually detaches from the rock. It dissolves completely.
It becomes a ghost.
Yeah.
It's no longer a solid mineral. It's a dissolved ion riding the groundwater currents invisibly.
Yeah.
And because it's soluble, it can travel for tens or even hundreds of miles through porous underground aquifers.
It will travel continuously as long as the water remains oxygenated.
Right.
But eventually, that groundwater is going to flow into a different geological neighborhood. It might hit a layer of rock that is rich in organic carbon like ancient decaying plant matter, a coal seam, or even a zone rich in iron sulfide minerals.
Environments that are reducing because the carbon and the sulfides eagerly consume any available oxygen.
Correct. The moment that oxygen-rich, uranium-carrying water hits the reducing boundary, the chemical environment flips.
Instantly.
Instantly. The organic carbon, or the sulfide, acts as an electron donor, forcing electrons back onto the uranium atom. The uranium drops from the soluble +6 state back down to the insoluble +4 state.
So it loses its solubility instantly.
Yes. The dissolved ghost suddenly precipitates out of the water, crystallizing as a heavy, solid mineral, typically uraninite or pitchblende, right there in the pore spaces of the rock. It drops out of solution and cannot move any further.
That is brilliant. It's exactly like a chemical toll booth.
It is.
And because groundwater might flow through that exact same carbon-rich choke point for millions of years, continuously dropping off its payload of uranium atom by atom, the uranium begins to stack up.
It concentrates.
Right. The sources detail a visual manifestation of this called roll-front deposits, which I found totally fascinating because they look like a freeze frame of this ancient chemical battle.
Oh, roll-front deposits are geochemically beautiful. Imagine a cross-section of a porous sandstone aquifer.
Okay.
As the oxygenated uranium-rich water pushes through the sandstone, it encounters a reducing zone of organic matter. The uranium precipitates out at the boundary, just like we talked about.
Right, it drops out as solid ore.
But over thousands of years, the continuous flow of fresh oxygenated water slowly oxidizes the carbon as well, gradually eating away at the boundary itself.
Oh, so the oxygen front keeps advancing.
Exactly. The boundary slowly rolls forward through the rock.
So the uranium precipitates, but then the oxygen front catches up, redissolves it, pushes it a few inches forward into the remaining carbon, and it precipitates again, over and over.
Exactly. It's a localized cycle of dissolution and precipitation that slowly marches through the aquifer. And what it leaves behind is a massive, highly concentrated band of solid uranium or curving through the rock in a crescent moon or a C shape.
That is so cool.
If you expose a cross-section of the rock in a mine, you can physically see the exact battle line where the oxidized, rust-colored rock meets the unoxidized gray rock with a thick band of black uranium ore marking the front line.
Wow. And the grades these processes can achieve are just staggering.
Yeah.
The literature points to the unconformity-type deposits, specifically in the Athabasca Basin in Saskatchewan, Canada, places like the Cigar Lake mine.
Yes. Very famous deposits.
The concentrations there completely defy typical mining logic. We're talking about ore grades hitting 15, sometimes 18% uranium by mass.
Just for context on how extreme that is for the listener, copper is routinely mined profitably at concentrations of half of 1%.
Half of 1%.
Right. Gold is mined at a few grams per metric ton. To have 18% of a rock mass be purely uranium is an extraordinary geochemical anomaly.
How does it even get that high?
Well, it occurred at Cigar Lake because of an incredibly stable, prolonged hydrological trap. Oxidized fluids from overlying sandstone, continually mixed with highly reducing fluids welling up from ancient basement faults.
So the two fluids were just constantly colliding.
Exactly. It created an unrelenting precipitation engine that ran for millions of years in the exact same spot.
But if we really want to bend our understanding of uranium geology, we have to look at the other major type of deposit detailed in the IAEA classification sources, the ancient quartz pebble conglomerates.
Oh, yeah.
Places like the Witwatersrand Basin in South Africa and Elliott Lake in Canada.
Mm-hmm.
Because the rules of the game for these deposits were entirely different. They formed in a world that doesn't exist anymore.
Yes, these are what we call paleoplacer deposits, and they are restricted to a very specific ancient window of time, mostly older than 2.2 billion years ago.
Okay, so deep time.
Deep time. If you look at the Earth's atmosphere before 2.2 billion years ago during the Archean eon, what is the critical missing component?
Free oxygen. This is prior to the Great Oxidation Event. Cyanobacteria hadn't yet evolved or proliferated enough to pump the atmosphere full of photosynthetic oxygen.
Precisely. The atmosphere was dominated by methane, ammonia, and carbon dioxide. Because there was virtually no free oxygen in the atmosphere, there was no dissolved oxygen in the rainwater or the rivers.
Right.
And if there is no oxygen...
The uranium cannot oxidize into that soluble +6 state.
Yeah.
It cannot dissolve.
Right. It remained locked in its highly stable, insoluble +4 state as the mineral uraninite. So as ancient granites weathered and broke apart from wind and rain, the uraninite crystals simply fell into the rivers as solid, incredibly dense grains of sand.
So it behaved exactly like gold. I mean, placer gold doesn't dissolve. It just gets physically washed downriver and settles in areas where the water current slows down just because it's so heavy.
That is exactly what happened with the uranium. The ancient river systems physically sorted the heavy uraninite grains. They tumbled along the riverbeds, dropping out of suspension in gravel bars inside the curves of meandering streams and in deep plunge pools.
Like nature's own gold panning sluice.
Nature essentially operated a massive physical panning operation, concentrating the heavy grains of uranium alongside actual gold grains. In fact, in the Witwatersrand today, uranium is often mined as a co-product of gold.
It's incredible to think about a riverbed sparkling with heavy black grains of uranium sand being sorted strictly by gravity rather than complex redox chemistry.
It really is a totally different paradigm.
It's a perfect geochemical timestamp, right? The very existence of these paleoplacer deposits proves that the ancient Earth lacked oxygen. Because once the Great Oxidation Event occurred and the Earth literally rusted, this physical panning process became impossible.
Right. Any exposed uraninite from then on immediately dissolved into the oceans.
It is a stunning example of how the evolution of life, photosynthetic bacteria, fundamentally rewrote the inorganic geology of the planet.
It changed everything.
And speaking of the intersection of life and uranium, we absolutely must touch on the biological mechanisms of uranium concentration, specifically regarding microorganisms.
Yes. The source material briefly notes bioreduction, and the implications of this are wild.
We're talking about bacteria, like Geobacter metalloreducens. They operate in exactly those anoxic, oxygen-starved environments we were just talking about. But they need to run their metabolisms, right? They need an electron acceptor.
Right. For us, that's oxygen. We breathe in oxygen, we use it to pull electrons down our metabolic chain, and we exhale CO2.
But what does Geobacter do when there's absolutely no oxygen around?
Well, Geobacter has evolved this extraordinary metabolic workaround called extracellular electron transfer. It can literally breathe dissolved metals.
Breathe metal. That is sci-fi stuff.
It sounds like it, yeah. In an anoxic groundwater environment rich in dissolved, oxidized uranium, the +6 state, the bacterium consumes organic matter, which is its food source, and strips electrons from it.
Right.
But instead of transferring those electrons to oxygen inside the cell, it uses specialized conductive proteins called cytochromes. And sometimes it even uses tiny conductive filaments called nanowires.
Nanowires.
Yeah, to physically push the electrons outside of its cell membrane and dump them directly onto the dissolved uranium ions floating in the water.
So the bacteria is acting as the reducing agent. It forces the electron onto the uranium, flipping it from +6 down to +4.
Exactly. And the consequence of that electron transfer is immediate precipitation.
Wow.
The soluble uranium instantly crystallizes as solid uraninite right on the outer surface of the bacterium. Over time, the bacterial colonies essentially encrust themselves in a shell of uranium ore.
They are living, metabolizing ore-forming machines.
Yeah.
They are literally pulling the ghost out of the water to power their own survival.
They are.
That blurs the line between biology and geology so completely. It really forces you to realize that a vein of uranium ore isn't just an inert rock. It is the end product of ancient river currents, the exhalations of photosynthetic algae shifting the global atmosphere, and the literal respiration of deep earth microbes.
It is a highly dynamic system, and the crazy thing is that dynamism doesn't stop once the ore is formed.
Right.
A primary deposit of pitchblende sitting deep underground is not the end of the story. If the geological conditions shift and new groundwater begins to penetrate that ancient ore body, a completely new phase of uranium chemistry begins.
Which brings us to the MDPI encyclopedic data. And this section blew my mind.
Right?
It's about a massive subcategory of minerals, the uranyl carbonates.
Yes. This represents the weathering and mobilization phase of uranium. If you have a solid primary ore body and groundwater seeps into it, the uranium will try to oxidize.
Right.
But groundwater isn't just pure H2O. It carries a heavy load of dissolved gases, predominantly carbon dioxide, often sourced from decaying organic material in the topsoil above.
So the water is slightly acidic and loaded with carbonate ions.
Right. And when this carbonated water interacts with the oxidized uranium, the uranium doesn't just dissolve and float away as a simple ion. The uranyl ion is intensely reactive with carbonates.
Oh, I see.
It bonds with them to form highly complex, often brightly colored fluorescent secondary minerals. These are the uranyl carbonates.
And the database lists roughly 40 approved distinct uranyl carbonate minerals. 40 different ways uranium can chemically stack itself with carbon and oxygen.
It's an entire architectural library of minerals.
And what struck me most is the speed and the aggression with which nature uses this exact mechanism to break down radioactive material. The sources highlight an incredibly dark but revealing modern example of this, the Chernobyl disaster.
Yes, Chernobyl is a perfect, albeit tragic, laboratory for this. In 1986, the catastrophic meltdown of Reactor 4 created a highly radioactive synthetic magma.
Corium, right.
Yes, corium. The uranium dioxide fuel rods melted and fused with the zirconium cladding, the steel reactor vessel, the concrete shielding, and even the sand dropped by the helicopters.
It's just a toxic stew.
It formed this highly toxic glass-like substance which flowed down into the basement of the plant and solidified. The most famous mass of this is known as the elephant's foot.
It is arguably the most dangerous, unstable, man-made material on the planet.
Yeah.
But nature doesn't view it with fear, right? To the Earth's geochemical cycles, corium is just an exposed, highly anomalous primary ore body.
Precisely. Geochemistry doesn't distinguish between a human disaster and a natural anomaly. It just sees the chemistry. As decades passed, rainwater, humidity, and atmospheric moisture, all of which carry dissolved carbon dioxide, slowly seeped into the ruined reactor hull and interacted with the surface of the corium.
Okay, so the water hits the elephant's foot.
Right, and scientists monitoring the ruins began to observe an efflorescence, a blooming of new, yellowish crystalline structures growing directly out of the synthetic lava.
And those crystals were uranyl carbonates.
They were. Nature was deploying the exact same chemical weathering toolkit it has used for billions of years to break down, stabilize, and eventually transport the uranium away. The corium was actively being digested and turned into complex secondary minerals.
That is wild. Let's break down the architecture of these minerals because the structural chemistry here is phenomenal. The source material spends a lot of time defining the fundamental building block of all these minerals, which they call the uranyl tricarbonate cluster.
Yes.
What does that actually look like at an atomic level?
So at the center, you have the uranyl ion itself. This is a single uranium atom bonded to two oxygen atoms, but importantly, the geometry is strictly linear. It forms a straight line. Oxygen, uranium, oxygen.
Like a rod.
Like a rod. Now, because uranium has a high charge, the equator of that uranium atom, the space right around its middle, is highly electropositive. It desperately wants to pull in negatively charged ions.
And the carbonate ions floating in the water are negatively charged.
Yes. So 3 flat triangular carbonate groups lock onto the equator of the linear uranyl ion. We call this bidentate bonding, meaning each carbonate attaches at 2 separate points, almost like molecular scaffolding, firmly gripping the central column.
Okay, so you have a rod in the middle and 3 triangles gripping it around the waist.
Exactly. This arrangement creates a hexagonal bipyramid. It is an incredibly stable, rigid, and perfectly symmetrical atomic cluster.
And that single perfect cluster becomes the core brick for building dozens of different minerals. Depending on what other elements happen to be dissolved in the groundwater, like calcium, sodium, magnesium, they act as the mortar, linking these uranyl tricarbonate bricks together into vast repeating crystal lattices.
That's the standard operating procedure for mineral formation, yes. But uranium chemistry doesn't always stop at simple repeating lattices. Under very specific conditions, it takes this self-assembly to an extreme that borders on architectural madness.
I love this part.
And the absolute pinnacle of this complexity is a mineral discovered relatively recently called euanite.
Euanite. The encyclopedia explicitly calls it the most structurally complex mineral on Earth. And when you look at the atomic diagram of this thing, it doesn't look like a rock. It looks like a biological virus or a synthetic nanomachine.
The complexity of euanite is staggering to mineralogists. Most minerals, like quartz or halite, have a very small unit cell.
A unit cell being the basic repeating pattern.
Right, a basic geometric box containing a handful of atoms that simply stacks endlessly in 3 dimensions. Euanite completely defies this simplicity. When the right ratio of uranyl ions, carbonate, calcium, and magnesium meet in a damp, oxidizing environment, they don't form a simple lattice. They spontaneously fold and link into a massive, self-contained nanocluster.
And massive being a relative term for the atomic scale, of course.
Yes, but in the realm of inorganic molecules, it is a behemoth. The euanite nanocluster is roughly 2.3 nanometers in diameter. A single cluster contains exactly 24 uranium atoms, 30 carbonate groups, along with precisely arranged calcium, magnesium, and hydration water molecules.
And they don't just clump together randomly. They actually form a cage, don't they?
They form an almost perfectly spherical, hollow geodesic dome.
Like Epcot Center.
Exactly like that. The uranyl bipyramids act as the structural joints, and the carbonates form the curved struts, all weaving together to enclose an empty, water-filled cavity. The thermodynamics required for this specific architecture to spontaneously self-assemble out of a cold, aqueous solution is a masterpiece of natural engineering.
It's unbelievable.
It requires a flawless balance of electrostatic forces and molecular geometry.
It is literally nature acting as a master molecular architect, building microscopic geodesic domes out of heavy metal and carbon, just quietly in the dark of a damp mine shaft.
It's beautiful.
And the larger implication here, the reason we care so deeply about uranyl carbonates in the first place is their mobility.
Exactly. Because these complex clusters are heavily bonded with water and carbonate, they are incredibly soluble. While a solid chunk of primary uraninite might sit stable in the rock for 1 billion years, once it weathers into a uranyl carbonate, it is primed to move.
It hits the road.
Yeah, these minerals are the chemical vehicles that allow uranium to leach out of rocks, enter the global groundwater system, and eventually flow into the oceans, completing its geochemical cycle.
Okay, so we have extensively mapped uranium's external life. We've seen how its electron shells make it surf magma, how it uses redox traps to form ores, and how it builds staggering atomic architectures with carbon.
Right.
But here's where we must pivot sharply, because while uranium is constantly engaging in all this complex external chemistry with the environment, deep inside the uranium atom, at the nucleus itself, an entirely different, completely independent physical process is occurring.
Yes, a process entirely divorced from temperature, pressure, or chemical bonding. We are talking about nuclear instability and the ultimate byproduct of that instability.
We're talking about the origin of the terrestrial helium supply, the party balloon, the MRI coolant, the solar ghost.
The connection between terrestrial helium and uranium is one of the most elegant stories in physics. To set the baseline, helium is the second lightest and second most abundant element in the entire universe.
Behind hydrogen.
Right. But the vast, overwhelming majority of the universe's helium, the helium that fuels the stars, was synthesized in the first 3 minutes of the Big Bang during the era of primordial nucleosynthesis.
Right. Space is just flooded with helium, but Earth is a small, rocky planet with relatively weak gravity. When the Earth was a swirling ball of molten rock, any primordial helium gas would have been far too light to be held by our gravity.
It would have boiled off and escaped into the vacuum of space immediately.
So the Earth essentially started with a zero balance of helium.
Zero. Which means every single cubic foot of helium gas we mine out of the ground today, every atom we use in industry, had to be manufactured internally by the planet itself after the crust solidified.
And the sole manufacturer of this gas is the radioactive decay of heavy elements, primarily uranium and thorium.
That's it.
Wait, I really need to pause and emphasize this for you, the listener, because it's so profoundly counterintuitive. We use helium to cool the superconducting magnets of life-saving medical devices. We use it for deep-sea diving gas mixtures. And yes, we put it in balloons. And 100% of that gas only exists on Earth because dense, intensely radioactive rocks have been slowly rotting away in the deep crust for billions of years.
It's an incredible thought.
To understand how a solid rock makes a light gas, we have to look closely at the physics of alpha decay.
Let's zoom in on the nucleus of a uranium-238 atom. It is monstrously huge. It contains 92 protons and 146 neutrons, tightly packed together.
That's a lot of particles in a tiny space.
It is. Now, in the nucleus, you have a constant battle between two fundamental forces of nature. You have the strong nuclear force, which acts like an incredibly powerful glue trying to hold all the protons and neutrons together.
Okay.
But because all 92 protons have a positive electrical charge, you also have extreme electrostatic repulsion. The protons are violently trying to push each other apart.
Because, charges repel. It's like trying to compress 92 incredibly powerful opposing magnets into a microscopic space. The tension is absurd.
Precisely. In a nucleus as large as uranium, the strong nuclear force is stretched to its absolute limit. It is barely overcoming the electrostatic repulsion. The nucleus is inherently unstable. It is vibrating, teetering on the edge of flying apart.
Right.
And eventually, through a process governed by quantum mechanics called quantum tunneling, a small piece of the nucleus manages to break the binding energy and escape. The uranium atom violently ejects an alpha particle.
Okay, an alpha particle radiation. But structurally, what exactly is an alpha particle?
An alpha particle is a highly stable, tightly bound cluster of exactly 2 protons and 2 neutrons.
2 protons, 2 neutrons.
And it gets shot out of the uranium nucleus at roughly 5% the speed of light. Now, if you look at the periodic table, an element is defined strictly by the number of protons it has. Hydrogen has 1, helium has 2.
So an alpha particle is not just generic radiation. It is literally a bare, naked helium nucleus.
Right. Exactly. It is a helium atom that has simply been stripped of its electrons. When it violently ejects from the uranium atom, it shoots through the surrounding rock lattice. It acts like a microscopic wrecking ball, smashing into other atoms in the rock, tearing their electrons away and losing kinetic energy with every single collision.
It's slowing down by stealing.
Yes. Once it slows down enough, it successfully captures 2 electrons from the surrounding environment. The moment it binds those 2 electrons, the electrostatic charge is neutralized. It calms down.
And the radiation ceases.
The radiation ceases. And what remains sitting quietly in the microscopic pore space of the rock is a perfectly stable, inert, elemental atom of helium-4 gas.
A gas atom born from the violent shedding of a solid rock atom. That's magic. And because the half-life of uranium-238 is 4.5 billion years, this is not a fast process, right? The rock doesn't just instantly turn into a cloud of gas.
Not at all. It is an excruciatingly slow, atom-by-atom trickle of helium generation occurring deep within the crust over vast stretches of geological time.
Okay, so then how do we get commercial quantities of it?
Over hundreds of millions of years, these individual helium atoms slowly migrate out of the crystal lattices and begin to seep upward through the crust. Because helium is so incredibly light and inert, it easily slips through microscopic fractures.
It just floats up.
Right. Most of it eventually reaches the surface and is lost to space. But sometimes its upward migration is blocked by a layer of impermeable cap rock, like a dense shale or a salt dome.
Oh, wait. Those are the exact same geological structures that trap natural gas and oil.
Exactly. The helium accumulates in these subterranean traps alongside methane. When petroleum companies drill into these ancient natural gas fields, they often hit massive pressurized reservoirs that contain 1, 2, or sometimes even 7% helium gas mixed with the methane.
And that's where we get it.
That is where all commercial helium comes from. It is a strictly non-renewable byproduct of geological time and radioactive decay.
And the history of how humanity figured this out is one of the greatest detective stories in science. Because we didn't discover helium by drilling for it on Earth. We had no idea it was under our feet.
No, we discovered it by staring at a star 93 million miles away.
The sun.
Yes. During a total solar eclipse in 1868, several astronomers, most notably Jules Janssen and Norman Lockyer, used a relatively new instrument called a spectroscope to analyze the light coming from the sun's outer atmosphere, the corona.
And spectroscopy relies on the fact that every chemical element, when heated, emits a very specific barcode of colored light, right?
Correct. Every element has a unique spectral signature. When Lockyer looked at the solar spectrum during that eclipse, he saw a brilliant yellow emission line that did not match the barcode of hydrogen, carbon, iron, or any known element on Earth.
It was totally alien.
It was. So Lockyer boldly proposed that they were looking at a completely unknown element that only existed in the intense heat of the sun. He named it helium, after Helios, the Greek god of the sun.
Makes sense.
For almost 30 years, helium was considered a purely celestial element, a solar ghost that simply did not exist on our planet.
So how did we finally find the ghost on Earth?
Fast forward to 1895. The brilliant Scottish chemist Sir William Ramsay was experimenting with a heavy, highly radioactive black mineral. He wanted to analyze the trace gases that might be trapped inside the rock.
Okay.
So he treated the mineral with sulfuric acid, dissolving it. As the rock broke down, it released a tiny bubble of trapped gas. Ramsay collected the gas, passed an electric current through it, and looked at the resulting light through his spectroscope.
And he saw the barcode?
He saw the exact same brilliant yellow line that Lockyer had seen in the sun 3 decades earlier.
And the radioactive rock Ramsay dissolved?
It was a mineral called cleveite. It is a highly impure, oxidized variety of uraninite, a uranium ore.
Wow.
Ramsay proved that the solar element existed on Earth specifically because he happened to dissolve a piece of uranium that had been silently decaying and stockpiling alpha particles in its crystalline structure for millions of years.
And you cannot write a more poetic scientific narrative. The heaviest, most earthbound, dense rock hiding in the dark crust is the sole parent of the lightest, most ethereal, star-forged gas we know of. It's brilliant.
It is a beautiful full circle.
But while this slow, steady, atom-by-atom alpha decay is fascinating, uranium possesses another, far more dramatic capability. It doesn't always just quietly decay. Under the right conditions, uranium can trigger a violent, cascading atomic chain reaction.
Which brings us to our final source, the Duke Energy article detailing one of the most staggering geological anomalies ever discovered, the Oklo natural nuclear reactors.
Let me set the stage for this because it sounds like pure science fiction. The year is 1972. Analysts at a nuclear fuel processing plant in France are doing routine mass spectrometry on a shipment of uranium or extracted from the Oklo mine in Gabon, West Africa.
Right.
They're measuring the exact ratio of the different uranium isotopes in the ore. Now, establish the baseline for us. What is the universal constant they expected to find?
Everywhere on Earth, whether you mine uranium in Canada, Australia, or Kazakhstan, the isotopic ratio is identical. The vast majority of the uranium is the stable isotope U-238, but exactly 0.7202% of the uranium will be the lighter, highly fissile isotope U-235.
So 0.7202%.
Yes. It is a hard, mathematically predictable constant.
But when the French scientists ran the Oklo ore through the spectrometer, the U-235 concentration wasn't 0.7202%, it was depleted.
It was.
Some samples measured 0.717%, and later samples from deep in the mine were as low as 0.44%. The U-235 was physically missing.
And in the highly regulated, deeply paranoid world of international nuclear materials, missing U-235 is the ultimate red flag.
Oh, absolutely.
U-235 is the isotope used to build nuclear weapons and fuel modern power plants. If the natural ratio is altered, the immediate assumption is human interference. Someone has secretly diverted or stolen the fissile material.
Right. The French Atomic Energy Commission essentially launches a massive investigation preparing for a major geopolitical incident. But as they analyze the ore further, they realize the material wasn't stolen by spies. They look at the trace elements left in the rock alongside the uranium, and they realize the U-235 was missing because it had been consumed. It had been burned in a nuclear chain reaction.
But there were no human reactors in Gabon. The geological evidence proved definitively that the fission had occurred spontaneously roughly 2 billion years ago. The rock itself was a nuclear reactor.
Okay, this is where I have to play the skeptic for you, the listener. How is that physically possible? A modern nuclear power plant is an incredibly complex marvel of high-end engineering, requiring purified water, control rods, and heavily processed fuel.
Yeah.
How does a damp pile of sandstone and dirt accidentally build a functioning nuclear reactor?
It requires an impossibly precise convergence of geology, hydrology, and nuclear physics.
Yeah.
To understand how Oklo functioned, we first have to solve the fuel problem. You mentioned that today, natural uranium contains 0.72% fuel. The chain reaction will die instantly. Modern reactors require the uranium fuel to be artificially enriched in centrifuges until the U-235 concentration reaches roughly 3%.
So if nature only provides 0.72%, how did Oklo run?
We have to factor in deep geological time and the laws of radioactive half-lives. Both U-235 and U-238 are unstable and decaying, but they decay at drastically different rates.
Okay, how different?
U-235 has a half-life of about 700 million years, while U-238 has a half-life of 4.5 billion years. Because U-235 decays much faster, if you run the clock backward, the ratio of U-235 to U-238 steadily increases.
Ah, I see where the math leads.
Exactly. 2 billion years ago, there was vastly more U-235 in existence than there is today. If you calculate the natural abundance of U-235 during that specific era, it wasn't 0.72%, it was approximately 3%.
Meaning 2 billion years ago, the natural background uranium on Earth was already enriched to the exact specifications required to fuel a modern commercial reactor.
Yes. No centrifuges required. The ore was reactor grade by default.
That is just wild. So the fuel was sitting there in the Oklo sandstone, incredibly concentrated thanks to the redox traps we discussed earlier.
Right, the concentration is key.
But fuel alone does not a reactor make. If a U-235 atom undergoes spontaneous fission, it spits out 2 or 3 neutrons. These neutrons are moving extraordinarily fast, around 10,000 miles per second.
Very fast.
At those speeds, the probability of a fast neutron cleanly striking another U-235 nucleus and causing a second fission event is incredibly low. It will likely just bounce off the U-238 or escape into the rock. The chain reaction fails before it begins.
To sustain a reaction, you have to slow the neutrons down. You need what nuclear physicists call a moderator.
Okay, a moderator.
Exactly. You need a medium that the neutrons can bounce through, losing kinetic energy with each collision until they reach a thermal speed. And at that speed, they are moving slowly enough to be easily captured by a U-235 nucleus.
Right, like billiard balls transferring momentum.
Yes. In modern reactors, we often use heavy water or ultra-pure graphite as a moderator. At Oklo, nature used ordinary groundwater.
So the groundwater just seeped down through the porous sandstone faults and saturated the highly concentrated uranium ore body.
Right. And because water is packed with hydrogen atoms, which are roughly the same mass as a neutron, it is highly effective at elastic scattering. A fast neutron hits a water molecule, transfers some energy, bounces, hits another, and slows down.
Well, let's put it all together. The ore is saturated. A U-235 atom spontaneously splits.
The fast neutrons hit the groundwater, slow down to thermal speeds, and are immediately absorbed by neighboring U-235 atoms, causing them to split.
Which releases more neutrons.
Which the water slows down, splitting more atoms. An exponential, self-sustaining nuclear chain reaction ignites deep underground. The rock literally turns on.
It's generating massive amounts of nuclear heat, which immediately raises the terrifying question. Why didn't it explode? If you have an uncontrolled exponential chain reaction in a confined underground space, it should escalate until it melts down or blows the surrounding rock apart like a dirty bomb. How did it regulate itself?
It utilized a brilliant, entirely passive thermodynamic safety mechanism, what engineers today call a negative void coefficient.
Negative void coefficient.
Yes. As the chain reaction ramped up, the immense heat began to boil the groundwater that was saturating the ore. The water phase changed into steam.
Wait, if the water boils into steam, it expands and becomes much less dense. It essentially leaves the immediate pore space of the rock. But the water is the moderator.
Exactly. As the water boiled away, the moderator vanished. The newly released neutrons were no longer being slowed down by liquid water. They remained fast neutrons, failing to trigger further fission.
Oh my God. By boiling the water, the reactor effectively pulled its own control rods out. It starved itself of the moderator and shut the chain reaction down completely.
It is an incredibly elegant negative feedback loop. The reactor shuts off and the rock begins to slowly cool. Over hours or days, the heat dissipates into the surrounding geology. Eventually, the rock cools below the boiling point. Fresh groundwater seeps back into the sandstone fractures, saturating the ore once again.
The moderator returns.
The moderator returns and the reactor turns back on, boiling, shutting down, cooling, turning on. It is estimated that these Oklo reactors operated in this pulsating cyclical manner for several 100,000 years.
It is the ultimate natural geyser, but powered by atomic fission instead of magma.
It really is.
And this wasn't just a single localized anomaly, right? The French didn't just find one hot rock.
No, subsequent geological mapping of the region identified at least 16 distinct separate reactor zones within the Oklo deposit and the adjacent Okolobando deposit. It was a sprawling subterranean complex of natural nuclear boilers.
Now I have to ask the obvious, slightly paranoid question. Is there any chance that somewhere deep in the Amazon or under the Canadian tundra, there is a natural nuclear reactor pulsing away right now?
Definitively no. The physics of our planet simply no longer permit it.
Because of the fuel ratio.
Right. Because 2 billion years have passed, the U-235 has continued its relentless radioactive decay. The natural abundance is now permanently locked at 0.72%. At that concentration, ordinary water absorbs too many neutrons relative to the number of fissions occurring. You cannot sustain a chain reaction with 0.72% uranium and regular groundwater, no matter how perfectly the geology aligns.
So the window closed.
The temporal window for nature to build a reactor closed over 1 billion years ago. Oklo is a magnificent relic of a bygone physical era.
But the Duke energy source explicitly points out that while Oklo is ancient history, the data we extract from it is intensely critical to modern human survival. It solves one of our biggest technological anxieties.
It does. The great Achilles heel of modern nuclear energy is the waste. When you split uranium, you generate a highly toxic cocktail of radioactive fission products, isotopes of strontium, cesium, iodine, technetium, and plutonium.
Really nasty stuff.
Very nasty. We engineer deep geological repositories to bury this waste, but public anxiety always centers on the long term. People always ask, how can you mathematically guarantee that this buried radioactive waste won't slowly migrate through the rock over the next 10,000 years and poison the groundwater?
Right. We can't run a 10,000-year lab experiment to prove our containment vessels work. Human civilization isn't old enough.
But Oklo already ran a 2-billion-year experiment. The natural fission at Oklo generated several tons of the exact same radioactive fission products and transuranic elements that our modern reactors produce.
The exact same waste.
The exact same waste. Since the 1970s, geochemists have painstakingly sampled the rocks surrounding the Oklo reactor zones to track how far those deadly isotopes migrated over the last 2 eons.
And the results of that tracking.
The results are astounding. Despite being subjected to millions of years of groundwater flow, tectonic shifts, and the immense heat of the reactors themselves, the most dangerous transuranic elements, like plutonium, barely moved a single millimeter from where they were originally synthesized.
A millimeter. In 2 billion years.
Exactly. The surrounding clay minerals and the solid uraninite crystal lattice itself acted as an impregnable containment vessel. The radioactive byproducts remained perfectly locked in the rock matrix, safely decaying into stable elements over millions of years. Oklo is the ultimate, undeniable proof of concept that deep geological storage of high-level nuclear waste is fundamentally safe and physically viable. Nature proved it.
It really is a complete closed narrative loop. The Earth demonstrated how to successfully enrich the fuel, moderate the reaction, operate the plant, and safely dispose of the waste, all completely blind, and 2 billion years before we split our first atom.
It really demands a profound respect for the deep geochemical cycles of the planet.
It absolutely does.
Yeah.
So let's step back and look at the sheer scale of the journey we've traced today. We started 4.5 billion years ago with the densest rock on Earth stubbornly refusing to sink to the core, its electron shells locking it to a buoyant raft of silicate magma.
We watched it get continuously rejected from crystallizing minerals, squeezed upward to the planet's surface like an unwanted puzzle piece. We saw it tumble as heavy sand down oxygen-free rivers in the deep Archean eon, alongside ancient gold.
We saw it become an invisible, soluble ghost riding the underground aquifers, only to crash into carbon traps and precipitate into massive crescent moons of solid ore. We watched metal-breathing bacteria use it to survive, and we saw it construct staggering 2.3 nanometer geodesic domes out of carbon dioxide and water.
It pulsed and boiled as a subterranean nuclear power plant, generating heat and trapping its own waste perfectly within the clay.
And quietly, underneath all of that dynamic chemistry, it spent 4.5 billion years relentlessly decaying. Atom by atom, struggling against the strong nuclear force, spitting out alpha particles that stole electrons from the rock to become the helium gas we rely on today. Which brings us right back to the beginning. The party balloon, the floating red foil. I want to leave you with one final thought, something to mull over that ties this all together. Because Earth's helium is created exclusively by the excruciatingly slow decay of uranium locked deep in the crust. And because helium is so incredibly light and inert that once it is released into our atmosphere, it completely escapes the pull of Earth's gravity.
Forever.
Forever. Every single time you let go of a helium balloon and watch it disappear into the sky, you aren't just losing a plastic toy. You are taking a tangible piece of the Earth's deep, ancient, radioactive history, a gas that took billions of years to forge in the dark, and you are venting it permanently, forever, into the void of space.
A ghost from the deepest crust, finally returning to the stars.
Something to think about next time you're at a birthday party.